So today I'm going to talk a little bit more about optimization problems. We're going to talk about Lagrange multipliers, and then after that we'll talk about integration. Okay. Okay, so let's talk about Lagrange multipliers first. So the problem which we're trying to solve is we want to find extrema of some function f of xy, but we're going to be constrained by an equation. So like x and y will be constrained to satisfy this equation as we're looking for the extrema. Okay. And so the procedure for solving this problem it's based off a theorem which says that if x naught y naught, or let's word it like this: if f has an extrema at some point x naught y naught, and then subject to this constraint, then the gradient of f evaluated at this point should be some multiple of the gradient of g evaluated at this point as well. Okay. So this symbol, it's a Greek letter lambda, and so it's what they refer to as the Lagrange multiplier. So basically, this is saying that if you have an extrema at this point, then the gradient vector of f should be parallel to the gradient vector of g at this point, is what it's saying. Okay. So that's sort of like a theorem, if you will. So then when you're looking for extrema, it amounts to trying to solve this equation. All right, so you need to solve this equation, which in terms of the components, this is saying like fx would need to be lambda gx, and fy would be lambda gy. Okay. So then ultimately, you need to solve this system of equations to find the extrema. So you have these two equations from the theorem, and then you always have your constraint equation as well. All right. So with Guanche multipliers, you'll basically set up the system of equations, and then the difficulty will come in trying to solve them. All right. So we'll do 2 examples is what I'm kind of planning. All right. So first, let's try to find extrema of the following function. F of xy equals, we'll do 3x minus 4y. And that'll be subject to the constraint x squared plus y squared equal to 1 to start with, okay? This one would be a sort of relatively simple problem to start with, just to illustrate, okay? Okay, so we have our function f of xy. From our constraint, the function g of xy would be x squared plus y squared. Okay. All right. Now, what we want to do is compute the partial derivatives inside of this system of equations. All right. So let's start by computing fx. So in this case, fx would just be 3. Fy would just be negative 4 in this case. Gx, partial g with respect to x, be 2x. And partial g with respect to y would be 2y, okay? Okay, so then right now what we have is fx, so 3 should be lambda times gx. And similarly, fy negative 4 should be lambda times gy. Okay. And then we have the constraint equation as well as our last equation, all right? So depending on how complicated the problem is, solving these equations to find the extrema could be a little bit difficult, all right? And I can't really give like a general strategy that will always work, because it's really going to be dependent on what functions you were given and then what the equations will look like because of that, okay? But one strategy that I commonly try, it works in a lot of examples, okay? Not all of them, of course, not necessarily, but it tends to work for a lot of examples. What I usually do is from these two equations, I solve for lambda in each equation. Is what I'm going to do, all right? So say like in the first equation, if I divide 2x to the other side, I would get 3 over 2x equals lambda. Now similarly, in the second equation, if I divide 2y to the other side, I'd have lambda is negative 4 over 2y, okay? All right, now before I continue, whenever you're dividing by a variable, when you're doing the Guanche multipliers, you want to be careful because you know that you can't divide by 0, right? So whenever you divide by a variable, you want to be cautious, I guess, and keep in mind that it's possible that the variable could have been 0. That could have been one of the solutions, all right? Now, this equation, in this particular example, you can see from this equation that x must be non-zero, because you have to get 3 on the other side. So that means we can safely divide by x, because we notice it can't be 0. And same for y as well. Okay. If I can't conclude that they must be non-zero, I would treat that as like a separate case. So like, if it looks like x might be 0, I can just plug in 0 for x here and solve for y to get the points. So it's not like a big deal if that happens. But yeah, so in this case, we're good. So once I do this, the idea is I have 2 expressions which are equal to lambda. So therefore, they should be equal to each other. All right. So I can then say, okay, so 3 over 2x should be equal to negative 4 over 2y. And then from here, I'm just going to cross multiply and simplify a little bit. So that'll be 6y is minus 8x. Okay. And what I want to do is either solve for y or solve for x. All right. Let's say I solve for y. So negative 8 over 6 would be negative 4 over 3x, okay? So the point of everything that I just did was to come up with a relationship between x and y, okay? Now once I get some relationship between x and y, then I'm going to sub it into my constraint equation, all right? All right. So the constraint was x squared plus y squared equals 1. So I'm going to do x squared. I'm going to replace y with minus 4 over 3x squared equals 1. Okay. And now what I can do is I can solve for x. So let's see here. I get x squared plus, that's going to be 16 over 9 x squared, right? Equal to 1. And let's add these together. So I'm going to do a common denominator. So we're going to get 25 over 9 x squared equal to 1. Okay. All right, so therefore x squared will be 9 over 25. So if we square root, we're going to get two solutions. X could be plus or minus 3 over 5. Okay? Okay, so we found our values for x. Now what I want to do is plug them back into this equation that we found earlier to get y. So when x is 3/5, we will get y is negative 4 over 3 times 3/5. Okay, so one point that we get, x is 3/5, and y is negative 4/5. Okay. And then when x is negative 3/5, so I'll plug that into y. And ultimately, we get the point x was negative 3/5. And here y would be positive 4/5. Okay? Okay. So these were sort of like our critical points, if you will. So now, like for this type of problem, I guess, what I want to do is plug them into my function now to see like which one was the largest and which one was the smallest. That will tell me like which one's the max and which one is the min. Okay. So then finally, our function f of xy. What was it again? 3x minus 4y. Okay, so let's plug in the first point. X is 3/5. Y is negative 4/5. Okay. So that will give me 9 over 5. So it's going to be plus 16 over 5. All right, so 25 over 5, it'll be equal to 5. Okay. If I do the other point, negative 3/5, positive 4/5, it's going to be the negative of everything, so it's going to be negative 5. Okay. So then, in this problem, looks like f will have an absolute maximum then. So it has an absolute maximum value of 5 at the points 3/5 and negative 4/5. Okay. And then you can say that it has an absolute minimum value of negative 5, and that happens at the point negative 3/5 and positive 4/5. Okay? So that would be the absolute maximum subject to our given constraint that we had. Okay. All right, any questions about that? Okay, all right. Okay, so let's try doing another problem. Okay, so this one's going to be find the absolute extrema of following function, f of xy equals, I'm going to do x squared plus y squared minus 3xy. Find absolute of f over the region. I'll do x squared plus y squared less than equal to 1. Okay. Okay, so this question is actually kind of similar to some of the examples that we did last time, where it's finding absolute extrema of a function over a closed and bounded region. So if you might remember, there were sort of two parts to the problem. First is finding the possible critical points inside this region. So if I draw it real quickly, it's a unit disk, right? So first I want to look for possible critical points inside the circle. And then there's a second part where I needed to check critical points along the boundary separately. Okay. So to get the critical points on the inside, there all we did was compute the partial with respect to x and y and set it equal to 0. Okay. So let's see here, fx would be 2x, right? Minus 3y. Okay. And let's see, fy would be 2y minus 3x. Okay, so we got the partial derivatives. We're going to set them equal to 0. And so let's see what to do here. Okay, so let's maybe just, doesn't really matter. So I'll solve for x in the first equation. So x would be 3y over 2. Okay. And then I'm going to sub it into the second equation. So we have 2y minus 3 and times x. Oh, sorry, x is, 3 has y. Okay. So then we need that to be equal to 0. Okay, so you get 2y minus 9 over 2y is 0. So if I make this a 4 over 2, it's negative 5 over 2y equals 0. But then that would just force y to be equal to 0. Okay. So then if y is 0, then coming back to this equation that we had earlier, we have x is 3 has 0, so it would be 0. Okay. All right. So we found one possible extrema inside the region, so it's the origin. All right. Now for the second part, when we're looking for critical points along the boundary, so the boundary of our region would have been the circle x squared plus y squared equal to 1. Okay. So we talked about some different ways of finding extrema along the boundary last time. One method was to parameterize the boundary. Or if you just got the equation of the boundary, you can plug the equation into your function. So we had 2 examples, one of each of that. But you can also use the method of the Guanche multipliers as well in order to find the extrema. So whenever your boundary is just an equation like this, then you'll be able to use the Guanche multipliers to try to find the extrema. Okay? Yeah, so then basically this equation for the boundary is your constraint. So then we're going to do Lagrange multipliers. This is our g of xy. Okay. So we're going to do fx is lambda gx. Now fy is lambda gy. Okay. So I computed fx and fy earlier, so I'm just going to copy those down. Okay. So now we want to set fx equal to lambda times gx, which would be 2x, okay? And then similarly, I'm going to do lambda times gy, which would be 2y, okay? All right. All right, so now again, in order to solve the system of equations, so I'm going to do kind of similar to what I did in the previous question. I'm going to divide I guess I'll divide by 2x to solve for lambda. Okay. And here I'll be able to simplify a little bit. So I can break this apart as 2x over 2x, which would be 1. And then minus 3y over 2x. I'll write, maybe it doesn't really matter, but I'll write it as 3 halves times y over x, okay? All right, makes sense. All right. Now, I did say before that when you divide by a variable, you want to be wary that the solution might have been 0. Okay. Looking at these equations, I can't seem to rule out x equals 0, at least not right away to me. All right. So I'm going to consider this time that x might be 0. Okay. All right, so either I can divide by x to get this, or x was 0. Now if x is 0, then I can solve for y straight away in my constraint. So let's just do that right now. So we just get x squared plus y squared equals 1. So we have y is plus or minus 1, okay? So that gives me x is 0, y is plus or minus 1. That's 2 points that I'm going to check later to see if they might have been like the max or the min, okay? Now I'm going to do similar with the second equation as well, all right? So in the second equation, I can divide everything by 2y. So I'll get lambda is 2y minus 3x over 2y. Which here it looks like I can simplify similarly. 1 minus 3 halves, but this time it's x over y. Okay. All right, now I have the similar issue that since I divided by y, I can only do that if y is not equal to 0. and I'm not sure I can rule that possibility out, so then I consider it as a separate case. Okay. I guess if you're ever uncertain, it probably doesn't hurt to always just include it anyways, because at the end, you'll still be able to check which one gave you the biggest value and the smallest, and you'll still know who the maximum were at the end. Okay, so here, if y is 0, then again, look at your constraint. And you can solve for x, all right? So that gives me these 2 points, which I will consider at the end. Okay. So then otherwise, as before, we have like these 2 expressions equal to lambda. Okay. And we'll call that A and I'll call this B. So from these 2 equations, since I have 2 things equal to lambda, that means they should be equal to each other. So I'm going to get 1 minus 3 halves times y over x should be equal to 1 minus 3 halves times x over y. All right? All right, so do you understand what I did there? Yeah, okay. So this is kind of the strategy that I usually do, as I was saying. I solve for lambda from both equations, and then I take those expressions and set them equal to each other, because they're both equal to lambda, okay? All right, so then from there, I now want to get some relation between x and y. So right now, I can cancel the 1s, and then the negative 3 halves as well. So I really just gotta get y over x must be x over y. All right, so then y squared should be equal to x squared. So that gives me y could be plus or minus x. Okay. All right. So once I get this relation between x and y, I plug it into my constraint. Okay. So constraint was x squared plus y squared. I guess it doesn't matter, whether it was plus or minus, and it equals 1. Okay. So then that will give me 2x squared equals 1. So then solving for x, we're going to get x plus or minus 1 over root 2. Okay. Okay, so when x is positive 1 over root 2, well, here I have y could be plus or minus x. So that means y could be plus or minus 1 over root 2. And then similarly, when x is minus 1 over root 2, I get y could be plus or minus. So that means this time I will consider all possible combinations of them. Okay? So we have this point, and then this point, and then this point. Okay? All right, good. So then, altogether, we found quite a few critical points. Hold on, I think it's, okay. And so we had these 4 points here. It's supposed to be blue, but that's okay. Then we had 2 here, 2 here, and then the origin here, okay? All right. So I'm just gonna, so now we're at the point where we just plug all of them into our function. So then I'm just going to copy the function down for reference. So that was f. So the origin was the first point that we found. So we get 0. The next points that we found were these 4 points. Plus, minus, 1, 0. Plus, minus, 1. Okay, so let's plug those in. So at 1, 0, we're going to get 1. That's the same at negative 1, 0. And then I guess f of 0 plus or minus 1, I think will also give you 1 as well. Okay? Okay, and then finally we had these 4 points. So those will maybe be a little bit more interesting. So let's check 1 over root 2, 1 over root 2. Okay? So plug it in, we're going to get 1/2 plus 1/2. This would be, I guess, minus 3/2 altogether. So it's going to be negative 1/2. Okay? Let's see here. If I do positive 1 over root 2 and negative 1 over root 2, so still 1/2 plus 1/2. But this time it's going to be plus an additional 3/2. So if y is negative, this will become plus 3/2. So this would be 5 over 2 altogether. Okay? When they're both negative, looks like it'll get the same as the first one. It's going to be negative 1/2, okay? And then I missed one. Okay, so when x is negative and y is positive, it's minus 1 over root 2 and positive 1 over root 2. And I think this one gets you positive 5/2 again, okay? So then looking at all the values, negative 1/2 was the smallest. So your function has an absolute minimum value of negative 1/2. And it actually occurs at 2 different points, this point and this point, okay? And then 5/2 is the largest value, so it actually has absolute maximum value of 5/2. And that happens at these 2 points instead, okay? All right. So then when you're doing these types of problems, like finding absolute extrema over a closed and bounded region, if your boundary is an equation, you can use method of Lagrange to try to find the critical point on the boundary, okay? All right, any questions about that? Okay. So then I'm going to spend the rest of the review talking about integration. Now, I'm probably not going to do much review in terms of like integration techniques from like Cal 1, Cal 2. So I'm going to focus more on, I guess, kind of the idea. So regarding integration, there's a couple things I want to touch on. So I want to touch on double integrals, iterated integrals, and then this Fubini's theorem as well, okay? So I'm going to start with iterated integrals first. That's maybe the simplest idea to start with, so I'm going to start with that. So really, I'm just going to do an example. All right. Okay, so let's say I have something like this. Let's do integral maybe 0, 1, and I'll do maybe 2, 3. And then let's say I have some function that we're integrating. I'll do maybe like x, y minus 2x plus y. I'll do maybe dx and then dy. Okay. Okay, so when you have, this is what we call an iterated integral. So it's really like doing 2 integrals. So you have this integral on the inside, which you're going to evaluate first. And then whatever the result of the inside is, you need to integrate that with respect to y here from 0 to 1. Okay. So when you're doing this integration, it's going to be similar to partial derivatives. So the inside integral is with respect to x. So you're going to treat x as a variable and pretend all the y's were constants. Okay. So then let's try to work out what this will be. So let's do the integral on the inside. X is the variable. So we're going to get x squared over 2. And then y was a constant, so I'm just going to carry it over. Okay. And then minus 2x becomes minus x squared. And then y as a constant is going to pick up an x when we integrate it, right? Okay, good. So then next when we're plugging in these bounds, okay? So since this was an integral with respect to x, that means I want to plug these numbers into x, all right? So not y, but plugging it into x. Okay, so numbers are a little bit messy perhaps, but let's plug in, so 3 for x. I'm going to get 9 over 2y minus x squared will be 9. Okay, plus 3y, right? Okay. All right, and then I'm going to minus what we get when we plug in x equals 2. So when x is 2, we're going to get 2y minus 4 plus 2y. Okay. Is that good? All right. So now let's just work out the rest of the problem. So I'm just going to simplify the inside first. So first we have 9 halves y minus, oh, let's see here. Okay, so for all the y's, I'm going to give them all a common denominator of 2. So I'll go back a step. So we have 9 over 2y. I'm going to write this as 6 over 2y. Okay. And here I'm going to distribute the minus, so we're going to get minus 2y plus 4 minus 2y. Okay. And I wanted to get a common denominator on all the y's. So let's make this minus 4 over 2. Likewise, this would be 4 over 2. Okay. So then I can combine like terms. So 9 plus 6 is 15. It'll be minus 8, so it'll be 7 over 2y. And then minus 9 plus 4 will leave me with minus 5. All right, so now it's relatively simple. So just integrating that with respect to y. So it's going to be 7 halves times y squared over 2 minus 5y. Now we're going to plug in 0 and 1 for y. Okay. So if I plug in 1 for y, I get 7/4 minus 5. And then this time, when you plug in 0 for y, everything becomes 0. So then, ultimately, my final answer is 7/4 minus 5. Okay. All right. So in this class, you probably don't need, like, if you're somewhat rusty on your integration, you'll probably need to be able to do U substitution. You'll probably need to be able to do integration by parts. But you probably won't see much, if any, like partial fractions or trig substitution. So I wouldn't need to worry that much, if you will, okay? But if you are rusty, go back and at least review U sub and integration by parts. I think those are the ones you'll most likely encounter if you need them, okay? All right. Okay, so that's how iterated integrals work. They're basically like partial derivatives, but you're integrating instead of doing derivatives. All right. So now I want to talk about something related to iterated integrals, which is the double integrals. So this is actually kind of like slightly different from iterated integrals. Okay. Fubini's theorem makes a connection between the two of them. That's what will happen, okay? And so I do want to recall a little bit of integration from Cal 1 right now, okay? Okay, so you probably remember that if you have the graph of some function of y equals f of x, the area like underneath this curve to the x-axis, that area was defined to be the value of this definite integral. All right, familiar? Yes? Okay, all right. Now, you might remember that how do we compute this area? They talked about it a little bit in Cal 1. You didn't do much with this, but they talked about the idea of like breaking this up into like little rectangles. You remember that? Yeah. Okay. So you did this thing where you break it up into tiny rectangles, add up the area of all the rectangles, and that was the approximation of the area. When you sort of like took the limit, as like the rectangles like shrink, that limit gave you the value of this integral. But of course, we don't actually do that when we're evaluating integrals. So what do we do instead, right? We do the thing where we evaluate the integral by finding the antiderivative. And most people would use like capital F for the antiderivative, and then you plug in the bounds, right? So the fact that we can evaluate integrals by doing this, that was the so-called fundamental theorem of calculus. Okay. So the integral is supposed to be the area, and then this theorem tells us that we can calculate the area or this integral by doing this. All right. So there's something similar now. If we have a function of two variables, then we think of the function as representing like the z-coordinate, right? So then like let's say this is the graph of some function f of xy. Okay. Okay. And then let's say it has some region here in the xy plane. I'm just going to call it D. Okay. And just as how like here I was interested in the area beneath the graph, here I'm interested in like what's the volume beneath this graph, but above this region in the xy plane. Okay. So I'll try to draw sort of a picture of this. So maybe it goes like that. Maybe this is like a... Maybe it looks like this, and then this is maybe like okay, so something like that, all right? But you can see like there is some like volume here, and there's sort of like a box, but with a funny bottom and top. Okay, and so the volume of this region is what we consider the double integral of this function f of xy over the region D. Okay, D, all right. And then people usually write like dA over here as well. It's kind of a notation, really, okay? All right, so this is the double integral of a function over some region in the xy plane. And visually, it represents like this volume is what it represents, okay? So there's this idea like here, to get the area, you break it into tiny rectangles. There's a similar idea here, which I'm not going to go into really, but you can like break this region up into tiny squares and try to calculate like the volume above each square, okay? And then like do like the summation, bunch of stuff. But again, we don't actually want to do that to evaluate the integral. Okay. So in order to evaluate these double integrals, I want like a theorem that tells me how to evaluate it. So sort of like what's my analog of the fundamental theorem of calculus, if you will. Okay. So that was Fubini's theorem. And so I really like this, so I'm going to go into a little bit, all right? Not that much, but so I guess the question is how to evaluate this double integral. And so the answer is going to be Fubini's theorem. So I want to spend just a couple of minutes talking about that theorem, and then I'll try to do some examples after that. Now I want to recall something that we did in Cal 1 again. So there was a type of question that you had in Cal 1 where you're given a curve. And the question was, revolve this curve about the x-axis. And then what's the volume of this region? Okay. Do you maybe by chance remember like the formula or whatever?
It's like integral of 2 pi with someone.
Okay, yeah. Okay, so you're thinking of a surface area formula. Okay. So now the idea of this formula was I did break this into tiny disks. Okay. All right. So each disk is a cylinder, and the volume of a cylinder was like the area of the base times the height. And so the height was like a small change in x. Okay. So like that was for like this little disk. Okay. Cool. All right. Now, in this particular instance, the radius of each disk could be treated as like the y value, which would be your function itself. Okay. And then when you like add up all the volumes and take like the limit, it sort of boils down to doing the integral from a to b. And you're doing like pi, the radius was like f of x squared dx. That was the formula that you would end up getting to get the volume of this region, all right? All right, so the key here, I guess, is like why are we integrating this? That was like the area of a circular slice of this region. Okay. So you can sort of generalize this to like even more like complicated looking regions. So let's say it had a funny shape like this. Well, okay. Kind of, okay, that's a little too weird. Okay. But you know, something like that. Okay. We can maybe imagine this is in 3D, so maybe this is at some height A and this is at some height B. So if I look at a particular slice of this region, so at some fixed height Z, all right, let's say the area of this slice is A of Z, okay? I could get the volume of this figure by doing the integral from A to B, A of Z, dz. So that's effectively what we did up here. Now here all your cross sections were circles, so it was very nice. We could just do pi r squared. So like in general, like although this kind of works in theory, but if the areas are really funky, then we might not be able to do this, all right? But still, the idea holds. So I want to apply this idea to this problem of calculating this volume. Okay. And this would be Fubini's theorem. All right. I'm going to try and give a good picture of this. I'm going to try to make a big picture then. Okay, so right now I'm just going to start by drawing a rectangle in the xy plane. Okay, and here's B. Okay, so I have this rectangle R right now in the xy plane. And then I have the graph of some function floating up top. Okay. So I want to find the volume above this rectangle and beneath the graph. All right. Okay. All right. So according to this idea that we have here, all right, what I can do is, maybe I'll try to use a different color. So imagine if I take a fixed x value and I look at how it slices through this region. Oh, well. Okay, so here in green, I'm going to try to draw like what the slice would look like. And then there's some kind of a curve, and then okay, so and when I slice at this x value, I get this like little sheet kind of thing, all right? And if I let the area, if I call the area of the sheet A of x, then I could say that the volume, let's maybe switch back to that real quick. So I could say the volume of this region, okay, would be the integral integrating x from a to b. And I want to integrate whatever a of x is. Okay? All right. Okay, now let's think about what a of x is, okay? Well, so up at the top, I have this curve here, right? Okay. So in green, this area is like the area underneath a certain curve. So what is this curve? Well, we know that this curve is on the graph, so it has to be satisfying this equation. But what's happening is along this curve, x is constant, right? So like the equation of this curve is the same as this up here, but x is constant and like y is a variable running from like c to d, okay? So if I want to get the area underneath this curve, I can calculate the area by doing the integral of this function. Okay? That's kind of the idea. So so we have this integral that we were trying to evaluate, and we're saying that a of x, that area, could be evaluated as another integral. This would be like an integral, like integrating y from c to d. I want to integrate this function, which was f of xy. So I'm thinking of this as a function of y, as x was constant along this slice. And I'd be integrating with respect to y, okay? All right, so then, so the volume was, I would have denoted it like this perhaps. I said the volume is the double integral over this rectangle in the xy plane of my function f of xy. Okay. And so we're saying this double integral is actually equal to this iterated integral, is what we're saying. Okay? And if I were to I could do a similar argument if instead of starting by slicing at an x value, if I slice at a y value, then I would have gotten the same thing, but with x and y interchanged on the inside and outside. So you get that the double integral can be computed by evaluating this iterated integral. And then, as I was saying, I could have also done y on the outside, and then x on the inside. And that should also give me the same thing, all right? So that's Fubini's theorem. So we saw in that earlier example that we kind of know how to evaluate iterated integrals. So now this is our method of therefore evaluating double integrals, because they're kind of the same in this sense, all right? Okay. So then, for instance, you might get questions like, let's say, for instance, let's say you want to evaluate the double integral over some region R. Let's say we want to integrate, let's do x, y, e, x squared, okay? 70 parentheses. And then let's do dA, it's a double integral. And let's say R is the rectangle. Oh, and I don't know if you guys use this notation, but I'll use it. I'll explain it as well. So.
Yeah, we use that one.
You do?
Yeah, we use that one.
Okay, yeah. Do you know what that means?
Like the x is going from 0 to 1 and the y is going from 0 to
Yeah, that's it, yeah. Okay, good. Okay. And so you probably already knew it, but by Fubini's theorem, we can evaluate this double integral by doing the iterated integral. Here they're both 0, 1, so I can just do that. xy e to the x squared. And then also, I could do either dx dy or dy dx, and I should get the same thing either way. Okay? So I just chose to do x first, so let's focus on that. Alright, so y is being treated as a constant. So I'll tell you what, let's actually pull the y outside the integral. So I just want to focus on that integral there with respect to x, all right? Okay, so to evaluate this, we need to do u substitution, all right? So I'm going to evaluate it off to the side. Okay, so you can do this one a couple of different ways, but I'm going to do u is x squared, okay? All right, and so if you remember how u sub works, we need to compute du. So du is 2x dx, all right? And I already have x dx in my integral. So what I might do is divide the 2 to the other side. So half du is x dx. And then we're going to make our substitution. So this is integral. So we have e to the u. And then we replace x dx with the 1/2 and the du. Okay. All right. So that's just going to be 1/2 e to the u, where u was e to the x squared. Okay. All right. So now I want to plug that into my problem. So y, and then this integral became 1/2 e to the x squared. Okay? All right, so then from 0 to 1. Okay. So if we plug in 1 for x, we'll get 1/2 e to the 1. And then plug minus, and plug in 0 for x, so it'll be minus 1/2. Okay? All right. Okay, now at this point, everything in the parentheses is actually a constant. Okay? So I just need to integrate y, so it'll be y squared over 2. Okay? And then we just need to plug in 0 and 1 for y. So when I plug in 1 for y, it's going to be 1/2 in the front. And then minus 0. Okay. All right, so then this would be our final answer. Good? Okay, all right. So then we can also, thinking of double integrals as representing volume, I can also ask find the volume beneath graph. Let's do f of xy equals maybe let's do x squared plus xy plus y, okay? So find the volume beneath the graph of this function, and above the rectangle R, let's do 0, 1 again, but here let's do maybe 1, 2. Okay. All right, so it's very similar to the previous question, right? So the volume, we know it would just be the double integral, which then we know we can write it as an iterated integral, okay? So we'll do the iterated integral of this function. And again, it doesn't matter if I do x on the inside or y. Let's do y on the inside this time and x on the outside, okay? So if that's the case, then the bounds on y were 1 to 2. The bounds on x were 0 to 1, so we write it like that, okay? All right. So then from there, we're first integrating with respect to y. So that's going to be x squared y plus x y squared over 2 plus y squared over 2. Okay? All right. And then we have the bounds of 1 to 2 and dx. Okay, so remember, you want to plug these numbers in for y. Okay, so I'm going to plug in 2 for y, so it's 2x squared. This will now be plus 4 over 2, so 2x plus 4. Okay. And minus, and then I'm going to plug in 1 for y. So it's going to be x squared plus x over 2 plus 1 half. And then dx. Okay? Alright, and then just as before, we just want to simplify. So I have 2x squared minus x squared give me an x squared. Okay? We have 2x, and we're going to have minus half of an x. So 2 minus a half will be 3 halves. So we have 3 halves x altogether. And then we've got 4 minus a half. So 8 over 2 minus 1 over 2 leaves me with 7 over 2. Okay? All right. And finally, just integrating, it's x cubed over 3. Here we'll get 3x squared over 4. Then this would be 7 over 2x. Okay. Then plug in 1, and we're just going to get 1/3 plus 3/4 plus 7 halves. 0, everything becomes 0. So then this would be our final answer for the volume. Okay. All right, any questions about that? Okay. Let's see here. I'm not sure if you guys have done this yet, but I'll do an example. So we'll just one more example, all right? Okay, so let's say we want to, I'll do find volume underneath graph f of x, y, let's just do x squared plus y, okay? Line underneath f and above so I'm going to do above the region in the first quadrant, bounded by x plus y equals 1. Okay? It's a little bit different from what we've done, but let's try to see how we'll set this up, okay? So I'm going to draw a picture of my region. Okay. Okay, so it's in the first quadrant, and this is y equals 1 minus x. So it's a line, y-intercept is 1, slope is negative 1, so it's going to go basically straight down to 1 like that. Okay, so this triangular region is the region that is being described in the question. So the idea is like, I have this region in the xy plane. My function, its graph is like, somewhere up here. Probably doesn't look like that, but something like that, okay? So it's kind of like, finding the volume as we talked about before. Okay. Now, we've so far been focused on rectangular regions, right? But it didn't have to be rectangular. So let's see what happens when the region is not rectangular, okay? I don't think you guys had any, you might have had some problems like this in your assignment, but if not, you'll definitely see this a lot more in the future. So if you haven't seen it yet, this will just be like a peek into the future. Alright, so to get the volume, it should be the double integral over this region of our function. And I can evaluate the double integral as an iterated integral using Fubini's theorem. So if I drew something other than a rectangle here, I could have gotten a similar result still. That's kind of the idea. So how this works is, all right, so I can do it, x first on the inside, y on the outside. Or I could do, y on the inside and then x on the outside. I'll do both so you can see it, all right? So let me focus on this setup first. So I'm integrating y on the outside, and I have in my region that y will range from 0 to 1. So I'm going to put 0 and 1 in for my bounds on y, okay? Okay, now the idea of Fubini's theorem, we had the idea that like we would slice at a fixed value, and then to get like the area of this slice, you would express that area as another integral. Okay. Now this time, however, the bounds on the integral, bounds on x are not going to be from 0 to 1. Because you see that it starts at 0, but it stops at whatever this is. Okay? So if the equation of my line is x plus y equals 1, then I could get this x value by solving for x. It should be 1 minus y. Okay? So that means it bounds on x. They'll start at 0, but they're always going to go up to the line, which was x equals 1 minus y. So I'm going to have 0 up to 1 minus y, but it bounds on x. See? So I'm not sure if you dealt with having variable bounds yet.
Yeah,
okay, all right. So that basically happens when your region is not a rectangle. Okay? But aside from that, it's nothing too special. So you just want to integrate your function doing this iterated integral. Now I do also just want to take a look real quickly at what happens if we did it this way instead. Maybe I'll draw a separate picture for that. So this time I have x on the outside. So in my region, I do have x going from 0 to 1 altogether. Okay? So that is going to be my bounds on x on the outside. All right? So then the idea was like on the inside, to get the bounds. So the idea was like you view x as being constant for this inside integral. So like for a constant x, what were the bounds on y? So y will be bounded always below by 0, but it's always bounded above by the line.
I don't know if you're busy, but Kelly said she wants you to come to her office.
Okay, all right, thank you.
Okay.
I'm almost done, so I'll be right
Sure,
back.
yeah. I don't mean to bother you.
Yeah, thank you. Oh, something special. I'm in trouble, I'll bet. Okay, so if we just solve for y, so whatever x is, y is always going to be 1 minus x. So that would be the upper bound on y, and then we're just doing this integral. Okay. All right. So this is Fubini's theorem for like non-rectangular regions. So you can still do the order however you prefer, dx, dy, dy, dx. But note that this time the bounds don't like just switch, right? It's like it wasn't, I just carried 0 and 1 minus y over here. I had to change it according to my region. All right. So always draw the region to figure out how to set up the bounds on the integral. And then I'm just going to start this real quick. I won't finish it. But like here, if I'm integrating with respect to x, I'll get x cubed over 3 plus xy, right? And then when you plug in these bounds, you plug them in for x. So like that means you would plug in 1 minus y, and then you get cubed over 3. And then again, like replace x with 1 minus y. Okay. And then when you plug in 0, it's all 0. So then you'd be left with that. Okay. So really, it kind of works the same as before. Of course, this would be a little bit messy, but
Yeah.
all right. But I will end it there. All right.
Okay.
Okay.